All right. Welcome to Chapter 4, talking about aqueous reactions and solutions. And there's a lot here, so I'm going to try to go through this as fast as I can. There's just a lot of information to cover. But the good news is most of the stuff we're covering today you have already done, so this isn't going to be anything totally new, I don't think. Okay. So first of all, when we're talking about electrolytes, we are talking about substances that dissociate into ions when you put them in the water. Okay. And the main place that you've probably heard the word electrolytes before is when we're talking about maybe Gatorade or a sports drink or something like that. When we're talking about playing sports and getting dehydrated, that sort of thing, you need electrolytes, okay? And all that is, it's a fancy term for basically ionic compounds, usually ionic compounds. Now, sometimes it can be molecular. We'll get to that in a minute. But they're going to split apart into ions when dissolved in water. A good example of this is sodium chloride, NaCl. Sodium chloride is an ionic compound. When you put that into water, it immediately splits apart into Na plus and Cl minus, okay? And so that's known as an electrolyte. A non-electrolyte might still dissolve, but it doesn't dissociate into ions, okay? Now this is an important distinction, the difference between electrolyte and non-electrolyte and soluble and insoluble. We need to make that distinction, okay? So if something is an electrolyte, it's usually going to dissolve in a solution, okay? If something is a non-electrolyte, that doesn't necessarily mean that it's not going to dissolve, okay? So a non-electrolyte, I just want you to notice this, it may dissolve in water, okay? An example of that is sugar. Sugar is considered a non-electrolyte. It doesn't really conduct electric current when you put it into a solution because it's not splitting apart into its ions. So you've got a sugar molecule like C6H12O6. You put that into water, it's still C6H12O6. It doesn't split apart into ions like sodium chloride does. But the sugar still does dissolve in the water, okay? So something can dissolve even if it doesn't dissociate. You need to know the difference between those two words. Okay, so soluble ionic compounds tend to be electrolytes, and a lot of ionic compounds are soluble, some are not, okay? So we got to talk about that in a minute. But you can see what's going on here. I think I showed this to you last year if you were in my class. Notice here, when you put something like salt into water, the positive ions then are surrounded by water molecules, the oxygen, the negatively charged part of the water molecule, and the negatively charged chlorines are surrounded by the positively, slightly positively charged hydrogens, okay? Molecular compounds are going to tend to be non-electrolytes. Most of the time, the exception to that is acids and bases. If you have something like hydrochloric acid, when you put that into water, it does split apart, even though that's a molecular compound because you've got two covalent atoms there. Or you got a covalent compound between two things that have close electronegativities. But still, when you put these into water, they're going to dissociate into H plus and Cl minus, okay? All right, so acids and bases are kind of the exception. This chart right here, I think is helpful. Shows that the strong electrolytes, all ionic compounds are going to tend to be strong electrolytes, okay? If they dissociate in water, they're going to dissociate. If they dissolve in water, I'm sorry, then they're going to dissociate completely, okay? Molecular, the strong electrolytes are going to be the strong acids. The weak electrolytes are the weak acids and the weak bases, and there are no weak electrolytes for ionic compounds. And the non-electrolytes, again, there's none of those for ionic. Ionic compounds are strong electrolytes if they dissolve. And then molecular compounds tend to be non-electrolytes. You can see here all other compounds besides acids and bases. Okay, strong electrolyte versus weak electrolyte. A strong electrolyte is going to dissociate completely in water. A weak electrolyte only dissociates partially. Okay, now an example of I gave you an example of a strong electrolyte. NaCl and HCl are both examples of strong electrolytes. They completely split apart in water. Now, if you've got something like acetic acid, okay, when you put acetic acid into water, that is a weak electrolyte because it's a weak acid. So what that means is some of it will dissociate into H+, some of it will dissociate into C2H3O2-, but some of it is going to stay together. Okay? So you've got three possibilities there. And really this right here is probably not going to happen as much as this does. It's going to tend to stay together. That's a weak electrolyte. Okay? So it only dissociates a little bit. Some of it will dissociate, some of it will not. Okay. Strong electrolytes, again, are the strong acids, the strong bases, and the soluble ionic salts, the ones that will dissolve in water. So it's important to know what are the soluble ionic salts. And so here is a list of soluble and insoluble ionic compounds. Now, there's a more complete list that you have in your Ultimate Chemical Equations handbook. Okay? So we'll get to that in a minute. But this is a pretty good list for starters. Okay? And I gave you this list last year, and I think if you were in Ernst's class, you got this list as well. But basically, at the top here, it's telling you the things that tend to dissolve. Soluble means that they do dissolve. Okay? Soluble equals dissolves in solution. Okay? It may not be water necessarily. Usually we're talking about water when we say this. Okay? It dissolves in solution. And so, if you have a compound that contains a nitrate, so if the anion is a nitrate, then they are all soluble all the time. Okay? If you have a compound that has acetic acid, that is soluble all the time. Chlorine, bromine, iodine, and sulfate, you have to look there. Normally they're soluble, but if you have silver chloride or mercury chloride, actually I guess that would be mercury 1 chloride, and lead chloride, lead 2 chloride, those are not going to dissolve in water. Those would be insoluble. Okay, so those are the exceptions. The insoluble ionic compounds, the ones that tend to not dissolve, are S-, S2-, CO3 2-, so sulfide, carbonate, phosphate, hydroxide. Usually those will not dissolve in water, but some exceptions here, and you can see the exceptions. All right. So things to notice here. Remember, when we talk about precipitation, when we talk about something forming a solid and falling to the bottom, I think the analogy I gave my class last year was that when you do a double replacement, these two things find each other, and they won't let the water molecules keep them apart anymore. And so they precipitate to the bottom of the solution, and they have a happy union together as a solid. Okay? And they don't let the water split them apart. The things that have trouble finding love are the nitrates, the acetates, and then if you look down here, the ammonium ion and the alkali metals. Okay? Notice, those are exceptions on almost all of these. NH4+ and the alkali metals, NH4+. Okay? So if you have these things, if you have NH4+, if you have an alkali metal, if you have a nitrate, or if you have acetate, for whatever reason, these are kind of the things that they just can never really find love, okay? Maybe they smell bad, I don't know. But they are not ever going to precipitate with anything, okay? So you put these in a compound of something, put them into water, they are going to dissolve, period. They are soluble all the time, okay? They will never form or precipitate. So that's kind of helpful to remember those things. And then you basically you need to know this chart, okay? It's very important that you know this chart. All right, let's do a sample problem here. Acetone, CH3COCH3 is a non-electrolyte. Hypochlorous acid is a weak electrolyte, and ammonium chloride is a strong electrolyte, okay? What are the solute particles present in aqueous solutions of each compound? So first of all, acetone. It's a non-electrolyte, okay? So the acetone here, what they're asking is, once you put this into water, what does it look like, okay? The acetone, the solute particles are still just going to be CH3COCH3, okay? They look exactly the same because they don't break apart in water. That's because they are non-electrolytes, okay? Now, hypochlorous acid, HClO, when you put that into water, it's a weak electrolyte, okay? So you're going to have three different solute particles there. You're going to have a little bit of H+, okay? Just a tiny amount of H+. You're going to have a little bit of ClO-. It splits apart. But most of the time, you're still just going to have HClO, okay? It's a weak electrolyte, so it only partially breaks apart. And most of the time, you're going to have the HClO, okay? Now, NH4Cl, that is a strong electrolyte. That means that as soon as you put it in water, these two things break apart. Now remember, NH4 plus, that's one of our ones that's never going to find love. So you put that into water, and as soon as the chlorine can, it gets away from the ammonium. It says, sorry, I'm going to go be with water now. You're on your own, okay? And so these two things are going to completely split apart, and the only thing you're going to have in that solution then is NH4 plus and Cl minus, okay? So that's how that works. All right, another sample problem here. Oh, actually, this is the second part of that question. If 0.1 moles of each of the compounds is dissolved in solution, which one contains 0.2 moles of solute particles, which contains 0.1 mole of solute particles, and which one contains somewhere between 0.1 and 0.2? All right, let's go back here. So we've got this acetone here, okay? If you put, let me read the question again. If you put 0.1 mole of each compound into a solution, okay? So we put 0.1 moles, there we go, of the acetone into a solution. It's not going to split apart, so it's still going to be 0.1 moles at the end, okay? So the CH3, COCH3, still going to be 0.1 moles at the end, okay? Because it doesn't split apart into anything. Now, if you put the HClO into a solution, a little bit of it will break apart into H+, a little bit of it will break up into ClO-, but not all of it, okay? So a lot of it stays together. So if you start with 0.1 moles of this, you're going to end up with more than 0.1 moles, but not twice as much, because this isn't going to completely break apart. Now remember, with moles, we're counting things, right? Okay? So all we're doing here is we're just counting the number of particles that we have. So if all of this broke apart, all of the HClO broke apart, then we would have twice as many particles as we started with, right? If we had 10 HClO molecules and it completely broke apart, then we would have 20 particles there. 10 of them would be H+, 10 of them would be ClO-, okay? But they don't all break apart. Maybe 5 of them break apart, and then the other 5 stay together, so we end up with just 15 total at the end. So we started with 10, we end up with 15. So it's not going to be twice as much, but it's going to be more than 0.1 moles. So this is going to be between 0.1 and 0.2, okay? And then if we put the NH4Cl into a solution, 0.1 moles of it, when that gets put into water, all of it breaks apart, okay? And NH4 plus and Cl minus, and now we have 0.1 mole of this and 0.1 mole of this. And so if you add those up, you have a total of 0.2 moles of particles, because each of these broke apart into 2 pieces. Okay, so now you have twice as many moles as when you started. Okay, precipitation reactions. Precipitation reactions happen when you do a double replacement, okay, which is basically just a wife swap, is what we talked about last year. So basically what you're doing is the the two compounds are trading partners, okay? And if you have a precipitation reaction, when they trade partners, one of them becomes insoluble, and one of them, in other words, will not dissolve in water anymore. So this is, again, this is the love story where they find each other, and they get together, and they decide the water's not going to tear them apart anymore, and they fall to the bottom of the solution, okay? Already looked at this. I'm not sure why I had that on there twice, but there it is again. It's very important. You have to know it. Maybe that's why. They do not give that to you on the AP exam, by the way. You have to know. You have to know those solubility guidelines. Okay. All right. Classify the following ionic compounds as soluble or insoluble in water. First of all, we got sodium carbonate, Na2CO3. All right. Now, I already know what this one is because I remember something. I remember that sodium is an alkali metal. Okay? And the alkali metals never, ever, ever precipitate with anything. Okay? So if it's an alkali metal, you automatically know this is going to be aqueous or aqueous. All right? This is AQ. That means it is soluble in water. Okay, lead sulfate. PbSO4. Now we're going to have to look at our rules for this one, okay, to decide whether this one is or is not soluble. So if we go back over here, okay, SO4 is right here. SO4 2- is one of the compounds that typically is soluble, okay. Typically it does dissolve in water. But one of the exceptions here is Pb2+, okay. That's exactly what we have. So PbSO4, that is love, okay? The lead finds the sulfate, they like each other, they decide to precipitate out of the solution and not let the water keep them apart anymore. This is going to be a solid, okay? Insoluble. That means it will not dissolve in the water. All right? Again, hopefully this stuff is all coming back to you from last year. All right, so when we talk about double replacement, double replacement reactions are also called metathesis or exchange reactions. But we called these double replacement last year. I just want you to know that terminology because they might throw that at you on the AP exam, and that could throw you for a loop if you don't know that term, okay? So that's what that means. And it means to transpose. So what you have going there, again, is you've got swap, okay? So you've got silver nitrate down here. Now remember, nitrate never precipitates with anything, so this is aqueous or aqueous, dissolved in the solution. You've got potassium chloride, alkali metal, that never precipitates with anything. So this is also aqueous. But these switch, the Ag now goes with Cl, and you end up with silver chloride. Turns out that is insoluble, so that forms a solid and falls to the bottom. And then really what you have here, when we talk about net ionic, hopefully this will, you'll remember this when we talk about it. That's really K plus and NO3-. Those two things aren't really together. Just like the things on this side weren't really together because they were both aqueous. Okay. All right, molecular equation. So when we talk about a molecular equation, that's the kind that we're typically used to writing. Tell you what, I'm going to cut off the video here, and we'll start. This actually is going to be a two-parter. But I want to make sure this one doesn't get too long, and then we'll actually come back and talk a little bit about the, well, no, I changed my mind. I think I've got enough time here that I actually want to talk about, this ultimate chemical equations worksheet that you got, this monster of a packet that I gave to you. Double replacement reactions here, it's giving you some information on that. Now this is basically a lot of what we just talked about, but this is not bad reading. You don't need to worry about reversible reactions for right now. We're going to go into that in a lot more detail soon. This is a better solubility table, and I say better, it's more complete than the solubility table in your book. And actually it adds another one to kind of the loser column, for lack of a better word there. Chlorates. Chlorates are all soluble, okay? There's really no exceptions there. And it actually looks like with acetate there is one exception, and that is if you have an a silver acetate, and is that a plus? I'm gonna have to look into that because I didn't know that one. Or wait, no, that's a star. Okay, I'm sorry, that's a star. So those are going to be slightly soluble according to what it says down there, but not enough, I guess, to really classify it as soluble. Okay, so the acetates, Ag is sort of a gray area there. And then the ones that are mainly water insoluble, so you've got a bunch of those down there. Get rid of this. Okay, so that's that. Formation of a precipitate, that's what we just talked about, okay? But this goes into more detail, and we need to talk about this because it's been a while since we've talked about it. There are some different ways that double replacement reactions can happen, okay? You can have formation of a precipitate happen, and when that happens, you're basically just switching these things around. So an example here would be like silver nitrate plus potassium chromate, okay? It says all reactants are aqueous. Oops, back here. All reactants are aqueous. So we've got silver nitrate, that's going to be AgNO3, plus potassium chromate, K2CrO4. And these things are just going to switch. So then you get the K going with the NO3. You're writing your molecular equation here. That's still going to be aqueous. Forgot to label this one as aqueous. So then the one that forms a precipitate must be, if anything does, silver chromate. Okay? Silver chromate. You'd have to check your solubility rules to see if that does or does not form a solid. Okay? Because some of these, it says some of them do not go to completion. So if two aqueous or aqueous solutions form there, then really nothing happens, okay? There is no reaction. So that's that. Now I'm going to have to erase all this, I just realized. Sorry, hang on. Okay. So it's got some good examples there. The other thing that can happen is formation of a gas, and we talked about this last year. The common gases that get formed are listed right here. It would be good to know these as well, and we'll do some more practice with these. But H2S, CO2, SO2, and H3, and it tells when those form. Again, we'll practice more with this in class, and it gives some good examples here of when this happens, how this happens. So then you can have a gas being formed. Okay. You can also have a molecular species being formed. Okay. And a molecular species, basically, that's just a fancy way of saying if you have an acid-base type reaction, which we talked about these last year as well. Okay. When you have an acid-base reaction, then you basically just do a double replacement here. So you can see, like this example down here of weak electrolytes forming as products, you've got CaCH3COO2 plus HCl. And what happens there is the calcium goes with the chloride, right? So they switch places, and the hydrogen goes with the other anion, okay? And you end up with a weak acid over here. Now you don't need to know the difference between a weak acid and a strong acid yet. We're going to learn that in a day or two. But that's the idea there, okay? You're just still doing a wife swap on all of these double replacements, but you just have to know what type of wife swap you're doing, okay? And then acid-base neutralizations, if you do a strong acid, strong base, then you're going to end up with a salt and water, okay? This is a very important thing to remember. You've got acid plus base gives you salt plus water, okay? And then it gives you some examples of that as well, okay? So that's it for that. Just wanted to make sure that you remembered some of the different possibilities, and I know I'm rushing through this, but I'm just hoping that some of this comes back to you from last year. But that's basically double replacement, okay? And now what we need to talk about is writing net ionic equations and that sort of thing. So I'm going to go ahead and cut the video off here. Part 2, we'll talk about how to write those net ionic